Hello and welcome. In this video, we'll be diving deep into the world of exponential functions and logarithms, a cornerstone of the IBAAHL mathematics curriculum. By the end of this session, you will be able to define and graph exponential functions, model real-world scenarios using these functions, understand the significance of the mathematical constant e, and finally, grasp the concept of logarithms as the inverse of exponentiation. We'll start with the basics and build our way up to more complex applications and problem solving, including several worked examples and practice questions. Let's begin by understanding what makes an exponential function unique. You're likely familiar with polynomial functions, where the variable is in the base, like x cubed equals 27. In an exponential function, the variable, or unknown, appears in the exponent. The general form is f of x equals a to the power of x. Here, a is called the base, and it must be a positive number. Why? Because if a were negative, certain exponents would be undefined in the real number system. For example, what is negative 1 to the power of 1/2? It's the square root of negative 1, which is not a real number. So, to keep things consistent, we restrict the base, a, to be positive. Let's visualize this with a simple example. Y equals 2 to the power of x. Notice a few key features. The graph passes through the point 0, 1. This is because any positive number raised to the power of 0 is 1. As x increases, the y value grows very quickly. As x decreases, the y value gets closer and closer to 0, but it never actually touches it. This line that the function approaches but never reaches is called an asymptote. For y equals 2 to the x-axis, or the line y equals 0, is a horizontal asymptote. So to recap, we've defined an exponential function as one where the variable is in the exponent, established that the base must be positive, and identified the key features of its graph: a y-intercept at 0, 1, and a horizontal asymptote at y equals 0. Now let's generalize these observations. We'll look at the graphs of y equals a to the x for different positive bases, a. Here we have 4 graphs. The black one is our familiar y equals 2 to the x. The green one is y equals 5 to the x. The blue one is y equals 1/2 to the x. And the red one is y equals 1/5 to the x. Notice that all 4 graphs pass through the point 0, 1. This is a universal property of all functions of the form y equals a to the x, because a to the power of 0 is always 1. We can categorize these graphs into 2 types based on the base, a. If the base, a, is greater than 1, like 2 or 5, the function is increasing. As x increases, y increases. This is called exponential growth. The larger the base, the steeper the growth. If the base, a, is between 0 and 1, like 1/2 or 1/5, the function is decreasing. As x increases, y decreases. This is called exponential decay. The smaller the base, the steeper the decay. An interesting observation is that the graph of y equals 1/2 to the x is a reflection of y equals 2 to the x across the y-axis. This is because 1/2 to the x is the same as 2 to the negative x. We'll explore transformations like this in more detail later. So we've now seen how the base, a, determines whether an exponential function models growth or decay, and we've confirmed the universal y-intercept and asymptote. Exponential functions are incredibly powerful for modeling real-world phenomena. They describe situations where a quantity changes by a fixed factor over equal time intervals. To model more complex situations, we use a more general form. N equals b times a to the power of t over k plus c. Let's break down what each of these constants represents. The constant, c, represents the background level or the horizontal asymptote. It's the value that n approaches as t gets very large. For example, the temperature of a cooling object will approach the room temperature. The constant, b, represents the initial difference from the background level. So the actual initial value of n, when t equals 0, is b plus c. The constant, a, is the growth or decay factor. If a is greater than 1, we have growth. If A is between 0 and 1, we have decay. Finally, cos the time it takes for the difference between n and the background level to change by the factor, a. Understanding these parameters is key to interpreting and creating exponential models. We've now established the general form of an exponential model and the meaning of each of its components. Let's put this into practice with our first worked example. This is a classic exponential growth problem. A population of bacteria doubles in size every 15 minutes. If there are 1,000 cells at 8 a.m., we need to find the number of cells at 8:15 a.m. and 9:24 a.m. First, let's set up our model. We'll use the form n equals b times a to the power of t over k. We'll let t be time in hours, with t equals 0 at 8 a.m. The problem states the population doubles, so our growth factor, a, is 2. It doubles every 15 minutes, which is 1/4 of an hour, so k is 0.25. The initial population at t equals 0 is 1,000, so b is 1,000. This gives us the model n equals 1,000 times 2 to the power of t over 0.25, which simplifies to n equals 1,000 times 2 to the power of 4t. Now we can answer the questions. For 8:15 a.m., t is 0.25 hours. Plugging this into our model, we get n equals 1,000 times 2 to the power of 4 times 0.25, which is 1,000 times 2 to the power of 1, or 2,000 cells. This makes sense, as the population should have doubled. For 9:24 a.m., we need to calculate the time in hours from 8 a.m. That's 1 hour and 24 minutes, which is 1.4 hours. Plugging this into our model, we get n equals 1,000 times 2 to the power of 4 times 1.4, which is 1,000 times 2 to the power of 5.6. Using a calculator, this is approximately 48,503 cells. So we've successfully built an exponential growth model and used it to predict the population at different times. We've seen how to identify the growth factor, the time period, and the initial value from the problem description. Now let's tackle a decay problem, which often involves a background level. This is a more complex model. The temperature of a cup of coffee is modeled by the function theta equals 70 times 3 to the power of negative beta t plus 22. We need to analyze this model. Part A asks us to show that theta minus 22 follows an exponential decay. To do this, we need to rewrite the expression in our standard form, n equals b times a to the power of t over k. First, we subtract 22 from both sides. Then, we use the rule of exponents that says a to the power of negative x is 1 over a to the x. So, 3 to the power of negative beta t becomes 1 over 3 to the power of beta t. We can write this as 70 times 1/3 to the power of beta t. This is in the form b times a to the power of t over k, where b is 70, a is 1/3, and k is 1 over beta. Since our base, a, is 1/3, which is between 0 and 1, this confirms it's an exponential decay. Part B asks for the initial temperature. Initial means t equals 0. Plugging in t equals 0, we get theta equals 70 times 3 to the power of 0 plus 22. Since 3 to the power of 0 is 1, the initial temperature is 70 plus 22, which is 92 degrees Celsius. Part C asks what temperature the coffee will reach after a very long time. This is asking for the horizontal asymptote. As t approaches infinity, the term 3 to the power of negative beta t approaches 0. So the temperature theta approaches 70 times 0 plus 22, which is 22 degrees Celsius. This is the background temperature of the room. Part D is a bit trickier. We need to find the time it takes for the temperature difference between the coffee and the room to fall by a factor of 9. The temperature difference is theta minus 22, which we know is 70 times 1/3 to the power of beta t. We want this difference to be 1/9 of its initial value. The initial difference was 70, so we set 70 times 1/3 to the power of beta t equal to 70 times 1/9. Dividing by 70, we get 1/3 to the power of beta t equals 1/9. Since 1/9 is 1/3 squared, we can equate the exponents. Beta t equals 2. Solving for t, we find that t equals 2 over beta minutes. Finally, part E asks how beta would change if the coffee were in a thermos flask. A thermos flask is better insulated, meaning the coffee will cool down more slowly. This means the time it takes to fall by any given factor will be longer. In our model, this means K must be larger. Since K is 1 over beta, for K to be larger, beta must be smaller. A smaller beta value results in a slower decay. This example demonstrates how to interpret a complex exponential decay model, find initial values and asymptotes, and solve for time based on a given change. Let's look at another common application, depreciation. This is a form of exponential decay. A car costs $17,500 and loses value at a rate of 18% each year. We need to write a model for its value, V, after n years. When dealing with percentage changes, we need to convert them into a growth or decay factor. A loss of 18% means the car retains 100% minus 18%, which is 82% of its value each year. So our decay factor, A, is 0.82. The initial value of the car is $17,500. Using the simple form V equals K times A to the n, we can see that K is the initial value. Therefore, our model is V equals 17,500 times 0.82 to the power of n. Now let's find the value of the car after 20 years. We simply substitute n equals 20 into our model. V equals 17,500 times 0.82 to the power of 20. Using a calculator, this gives us approximately $330.61. That's a significant drop in value. This example shows how to translate a percentage decrease into a decay factor and use it to model depreciation over time. Let's work through another problem from the textbook Exercise 2B. Question 2. An algal population grows by 10% every day. The area it covers is modeled by y equals k times 1.1 to the power of t, where t is in days. We're told that at 9 a.m. on Tuesday, it covered 10 square meters. We need to find the area it will cover by 9 a.m. on Friday. First, let's find the value of the constant k. We know that at t equals 0, which will set as Tuesday at 9 a.m., the area y is 10. Plugging these values into our model, we get 10 equals k times 1.1 to the power of 0. Since 1.1 to the power of 0 is 1, we find that k equals 10. So our complete model is y equals 10 times 1.1 to the power of t. Next, we need to find the time, t, from Tuesday, 9 a.m., to Friday, 9 a.m. From Tuesday to Wednesday is 1 day. From Wednesday to Thursday is another day. And from Thursday to Friday is a third day. So t equals 3 days. Now we can find the area on Friday. We substitute t equals 3 into our model. Y equals 10 times 1.1 to the power of 3. This is 10 times 1.331, which equals 13.31 square meters. So by Friday, the algal population will cover 13.31 square meters. This problem reinforced how to find the initial value, k, and how to calculate the time, t, from a given start and end point. Let's move on to a more challenging problem, Exercise 2B, Question 3. This one involves finding multiple constants. The air temperature T around a light bulb is given by T equals A plus B times 2 to the power of negative x over k. we are given three pieces of information. The background temperature is 25 degrees, the surface temperature is 125 degrees, and the temperature 3 millimeters away is 75 degrees. We need to find the integer values of A, B, and K. Let's use the information to form equations. First, the background temperatures. The background temperature is the horizontal asymptote, which is the constant A in our model. So A equals 25. Next, the surface temperature. The surface is at a distance of x equals 0. We substitute x equals 0 and t equals 125 into our model. This gives us 125 equals 25 plus b times 2 to the power of 0. Since 2 to the power of 0 is 1, we have 125 equals 25 plus b. Solving for b, we get b equals 100. Now we have a and b. We can use the third piece of information to find k. The temperature is 75 degrees at x equals 3 millimeters. We substitute x equals 3, t equals 75, a equals 25, and b equals 100 into our model. This gives us 75 equals 25 plus 100 times 2 to the power of negative 3 over k. Subtracting 25 from both sides gives 50 equals 100 times 2 to the power of negative 3 over k. Dividing by 100 gives 1/2 equals 2 to the power of negative 3 over k. Since 1/2 is 2 to the power of negative 1, we can equate the exponents. Negative 1 equals negative 3 over k. This means k equals 3. So we have found the integer values of our constants. A equals 25, b equals 100, and k equals 3. This gives us the complete model for the temperature around the light bulb. This problem is a great example of how to use multiple data points to solve for the unknown parameters in an exponential model. Let's now introduce a very special mathematical constant, e. It's an irrational number, like pi, that appears naturally in many areas of mathematics and science. The constant, e, is defined as the limit of the expression 1 plus 1 over n, all to the power of n as n approaches infinity. Let's see what happens as n gets larger. If n equals 1, we get 2. If n equals 2, we get 2.25. If n equals 4, we get 2.44. The value is increasing, but it's not increasing without bound. It's approaching a specific number. This number is e, approximately 2.71828. It's often called Euler's number, after the famous mathematician Leonhard Euler. So what does this limit represent? It's the result of continuous compounding. Imagine you have a 100% interest rate over a year. If it's compounded once, you double your money. If it's compounded twice, you get 2.25 times your money. If it's compounded continuously, you get e times your money. The number, e, is the base of the natural logarithm, which we'll discuss shortly. It's also fundamental in calculus for describing rates of change. For now, remember that e is just a number, and all the standard rules of arithmetic and exponents apply to it. We've now defined the constant e as a limit and seen its approximate value. This constant is crucial for understanding continuous growth and decay. Now that we've explored exponential functions, let's introduce their inverse operation, logarithms. Just as subtraction is the inverse of addition, and division is the inverse of multiplication, logarithms are the inverse of exponentiation. Think about solving a simple equation like x squared equals 3. To find x, we use the inverse operation, the square root. We write x equals the square root of 3. Now consider an exponential equation like 2 to the power of x equals 8. You might know the answer is 3, because 2 cubed is 8. But what if the equation was 2 to the power of x equals 7? How would you solve for x? This is where logarithms come in. A logarithm is simply a way to ask the question, to what power must I raise this base to get this number? The equation 2 to the power of x equals 7 can be rewritten in logarithmic form as x equals log base 2 of 7. This statement means the exact same thing. X is the power to which you raise 2 to get 7. In general, the exponential equation b to the power of y equals x is equivalent to the logarithmic equation y equals log base b of x. The base b is the same in both forms. There are two special bases that are used so frequently they have their own notation. Base 10 is written as log of x, and base e is written as ln of x, which stands for the natural logarithm. So log of x is the power you raise 10 to get x, and ln of x is the power you raise e to get x. We've now introduced logarithms as the inverse of exponentiation, and learned how to convert between the two forms. This is the fundamental concept that will allow us to solve for variables in the exponent. Let's apply our new understanding of logarithms to solve some problems. We'll start with a problem from the textbook, Exercise 2b, Question 5. We are asked to find all values of x, for which y equals 3, given the function y equals 1 plus 16, to the power of 1 minus x squared. First, we substitute y equals 3 into the equation. This gives us 3 equals 1 plus 16 to the power of 1 minus x squared. Subtracting 1 from both sides, we get 2 equals 16 to the power of 1 minus x squared. Now we have an exponential equation where the variable is in the exponent. We can solve this by converting it to logarithmic form. Using our definition, the exponent 1 minus x squared is equal to log base 16 of 2. We need to evaluate log base 16 of 2. This asks, to what power must I raise 16 to get 2? Since the square root of 16 is 4, and the square root of 4 is 2, we can say that 16 to the power of 1/4 is 2. So log base 16 of 2 is 1/4. Now we substitute this value back into our equation. Now we have a simple quadratic equation to solve for x. Rearranging the equation, we get x squared equals 1 minus 1/4, which is 3/4. Taking the square root of both sides, we get x equals plus or minus the square root of 3 over 2. Remember to include both the positive and negative solutions. This example shows a complete process, setting up the equation, converting to logarithmic form, evaluating the logarithm, and solving the resulting algebraic equation. Let's try another problem, Exercise 2b, Question 6. This one involves exponential decay with a percentage decrease. A bowl of soup cools in a room at 20 degrees Celsius. Every 5 minutes, the temperature difference between the soup and the room decreases by 30%. The initial soup temperature is 55 degrees. We need to find its temperature after 7 minutes. First, let's identify the components of our model. The room temperature is the background level, so C equals 20. The initial temperature difference is 55 minus 20, which is 35 degrees, so B equals 35. The temperature difference decreases by 30% every 5 minutes. This means it retains 70% of its value, so our decay factor, A, is 0.7. The time period for this change is 5 minutes, so K equals 5. Our model for the temperature T is T equals 20 plus 35 times 0.7 to the power of T over 5. Now we need to find the temperature after 7 minutes. We substitute T equals 7 into our model. T equals 20 plus 35 times 0.7 to the power of 7 over 5. This is 20 plus 35 times 0.7 to the power of 1.4. Using the calculator, this is approximately 20 plus 35 times 0.588, which gives us a final temperature of about 40.58 degrees Celsius. This problem combines several concepts: a background level, an initial difference, and a percentage decay over a specific time period. We've seen how to assemble these pieces into a single model. Let's tackle another problem from the textbook, Exercise 2c, Question 1. This one involves the constant, e. We need to find the value of 5 times e to the power of 0.5 rounded to 3 significant figures. This is a straightforward calculation using a calculator. You'll need to locate the e button, which is often found by pressing Shift or second function and then the ln button. First, calculate e to the power of 0.5. This is approximately 1.6487. Then, multiply this by 5. This gives us approximately 8.2436. Finally, we round this to 3 significant figures, which is 8.24. This problem serves as a reminder that e is just a number, and we can perform standard arithmetic operations with it. The key is knowing how to use your calculator to evaluate expressions involving e. Let's look at a problem that requires us to think about the properties of exponents and logarithms. This is Exercise 2b, Question 12. We are given the equation 4 to the power of ax equals b times 8 to the power of x. We are told there is more than one solution for x, and we need to find all possible values of a and b. The key here is to express everything with the same base. Both 4 and 8 can be written as powers of 2. We can rewrite 4 as 2 squared and 8 as 2 cubed. Substituting these into the equation, we get 2 to the power of 2ax equals b times 2 to the power of 3x. Now let's rearrange the equation to isolate the exponential terms. Dividing both sides by 2 to the power of 3x, we get 2 to the power of 2ax minus 3x equals b. We can factor out x from the exponent, giving us 2 to the power of x times the quantity 2a minus 3 equals b. The problem states there is more than one solution for x. Let's analyze this equation. If the exponent, x times 2a minus 3, is not 0, then there will be only one solution for x. For example, if 2a minus 3 is 1, we have 2 to the x equals b, which has a unique solution, x equals log base 2 of b. For there to be more than one solution, the exponent must be 0. This happens if the term 2a minus 3 is 0. If 2a minus 3 equals 0, then a must be 3 over 2. In this case, our equation becomes 2 to the power of 0 equals b, which means b equals 1. So if a is 3 over 2 and b is 1, the equation is 1 equals 1, which is true for all values of x. This gives us infinitely many solutions, which satisfies the condition of having more than one solution. Therefore, the only possible values for a and b are a equals 3 over 2 and b equals 1. This problem required a deep understanding of exponent rules and the conditions for an equation to have multiple solutions. It's a great example of a higher-level thinking question. Let's work through one more problem, exercise 2c, question 7. This is a decay model involving the constant, e. The speed v of a parachutist is modeled by v equals 40 times the quantity 1 minus 3 to the power of negative 0.1 t. We need to find the initial speed and the speed the model predicts he will eventually reach. Part A asks for the initial speed. Initial means t equals 0. We substitute t equals 0 into the model. V equals 40 times 1 minus 3 to the power of 0. Since 3 to the power of 0 is 1, we get v equals 40 times 1 minus 1, which is 40 times 0, or 0 meters per second. This makes sense, as a parachutist starts from rest. Part B asks for the speed the model predicts he will eventually reach. This is asking for the horizontal asymptote as t approaches infinity. As t approaches infinity, the term 3 to the power of negative 0.1 t approaches 0. So the speed v approaches 40 times 1 minus 0, which is 40 meters per second. This is the terminal velocity of the parachutist. This problem is a great application of exponential decay to a physical situation. We've seen how the model correctly predicts both the initial state and the long-term behavior of the system. Let's conclude with a final problem, exercise 2b, question 11. This is a proof that relies on the properties of exponents. We need to prove that 2 to the power of 350 is larger than 5 to the power of 150. The numbers are too large to calculate directly. The strategy is to simplify the exponents by finding a common factor. The exponents are 350 and 150. The greatest common factor of 350 and 150 is 50. So, we can rewrite both expressions with an exponent of 50. Using the rule of exponents that says a to the power of m times n is equal to a to the power of m, all to the power of n, we can rewrite 2 to the 350 as 2 to the power of 7, all to the power of 50. Similarly, we can rewrite 5 to the 150 as 5 to the power of 3, all to the power of 50. Now, we can compare the bases. If the bases are larger, the overall number will be larger. Let's calculate the new bases. 2 to the power of 7 is 128. 5 to the power of 3 is 125. So our problem is now to compare 128 to the power of 50 with 125 to the power of 50. Since 128 is greater than 125, it follows that 128 to the power of 50 must be greater than 125 to the power of 50. Therefore, we have proven that 2 to the power of 350 is larger than 5 to the power of 150. This proof demonstrates a powerful technique for comparing large numbers by simplifying their exponents. It's a great example of how understanding exponent rules can lead to elegant solutions. We've covered a lot of ground today. We started by defining exponential functions and their key properties, including growth, decay, asymptotes, and intercepts. We then learned how to build and interpret general exponential models, n equals b times a to the power of t over k plus c, and applied them to real-world scenarios, like bacteria growth, coffee cooling, and car depreciation. We introduced the special mathematical constant, e, and saw how it arises from continuous compounding. Finally, we defined logarithms as the inverse of exponentiation and used them to solve for unknown exponents. To solidify your understanding, here are 5 practice questions. I encourage you to pause the video and try them on your own. Question 1. A population of 500 bacteria triples every 2 hours. Write a model for the population P after t hours and find the population after 5 hours. Question 2. The value of a painting, V, in thousands of dollars, is modeled by V equals 150 times 1.08 to the power of t, where t is the number of years since 2000. Find the value of the painting in 2015. Question 3. A radioactive substance decays such that its mass m, in grams, after t days, is given by m equals 200 times e to the power of negative 0.05 t. Find the mass after 10 days. Question 4. Solve the equation 3 to the power of 2x minus 1 equals 27 for x. Question 5. The temperature T of a cooling object is given by T equals 10 plus 50 times 0.8 to the power of T, where T is in minutes. What is the initial temperature? What is the room temperature? And what is the temperature after 3 minutes? Thank you for watching. Keep practicing these concepts, as they are fundamental to many areas of higher-level mathematics.